This car can lap 10 seconds faster than a Formula 1 car. It generates 1.5 tons of downforce, has half the drag of a modern F1 car, and can be built with technology that exists today. It could also be built for a tenth of the cost of a 2025 F1 car. So, who designed it? Meet Lucas Di Grassi, former F1 driver, Formula E champion, and the man behind this unusual looking machine.
So I was thinking, if I design a car from scratch, using just first principles, using new technologies that are not regulated, where could we get to?
And to do that, he used technology that was banned in Formula 1. But this isn't just a concept. This has been tested in a digital wind tunnel, driven in lap time simulation software, and the numbers are very impressive. So I spoke to Lucas to understand what just might be a better way to design a Formula 1 car, if there were no rules. So let's start with the frame Lucas was working within. He wanted to design something that was possible to build with today's technology. So everything on this car already exists. The battery packs, the motors, the carbon fibre. And before you click away, yes, this is an electric car. And I know we all love V10s, but stick with me here, because the engineering Lucas has done is genuinely fascinating. Let's start with the biggest issue when designing race cars. It's something Lucas calls the drone paradox.
Imagine that you have a drone, right? But then you want the drone to fly for a longer period. So you add battery in the drone. When you add battery in the drone, it becomes heavier. So you need bigger motors, which means the motors consume more energy. Therefore, you need a bigger battery, which requires a bigger motor. So actually, the flying time of a drone is kind of constant at 20 minutes, regardless of the motor or the battery size, because it's proportional.
And racing cars have a similar problem. Actually, they have two. First, if you want more range or more power, you need more fuel or more battery. But that means more weight. And that weight needs to be slowed down, turned, and accelerated. So you need more power to move it, which uses more energy, which means you need more fuel or battery. Plus, the heavier the car, the more downforce you need to go through a corner at the same speed as a lighter car. Which leads us to the second problem. In modern Formula 1, if you want to go faster through corners, you add more wing. But that wing creates drag all around the lap. That invisible pressure slowing the car from higher speeds. And drag gets worse really quickly. So if you double your speed from 100 to 200 miles an hour, the drag doesn't just double, it quadruples. 4 times as much force pulling against the car. And the frustrating bit is you don't actually need that downforce on the straights. You're just wasting energy dragging a big wing through the air at high speed, when you only really need grip under braking and in the corners. And this was Lucas's biggest issue to try and solve.
How do you gain downforce without gaining so much drag? Because as soon as you start putting wing up, you start generating drag. It's a function of the downforce.
So Lucas realised reducing drag should be the focus. If you can generate good downforce but create less drag, you solve the problem. You have a car that's quick in the corners, quick on the straights, and requires much less power to move it through the air at speed. But how do you do that? Well, the answer came from a couple of cars you probably already know. The Brabham BT46 and the McMurtry Sperling, but with even more innovation. These two cars are famous because they have fans to generate downforce. The Brabham won its first Grand Prix and then was instantly banned. But the McMurtry has broken lots of lap records, including Goodwood, and it can drive upside down. Granted, not through proper aerodynamics, only Project Inversion can do that. And by the way, we're still trying to make that happen. But what Lucas has done differently is combining 3 powerful aerodynamic systems that work together. A traditional ground effect floor, 2 electric fans, and a blown diffuser. And when you put them all together, the numbers are very impressive.
It's 5 times more efficient to generate downforce from an electric fan sucking the air underneath the car than it is from a wing.
So for the same amount of energy, you get 5 times as much downforce. Or to put it another way, to generate the same downforce, a fan uses 1/5 of the energy that a wing would. And we'll get into the maths on that a bit later. But let's understand how Lucas's system actually works first. So the ground effect floor. This is a proper racing car floor with tunnels and a diffuser, just like a modern F1 car. and that floor generates downforce naturally when air flows underneath it. Then Lucas has added two 30 kilowatt fans, one on each side of the floor, that creates suction underneath the car. At high speed, let's say 300 kilometers an hour, the natural aerodynamics of the floor are generating about 1.5 tons of downforce. And at that speed, the fans are switched off completely. But as you slow down for a corner, the natural downforce drops off. So for example, at 60 kilometers an hour, where natural aero is almost nothing, the fans are running at maximum power, adding that downforce back in to maintain 1.5 tons of downforce. And between those two speeds, it's a blend. As the car accelerates and the natural downforce builds, the fans gradually reduce power. It's not binary, it's not on or off, it's variable. And that means you're only using the fan power when you actually need it, which of course saves energy. The result is that the car has constant downforce all the way around the lap, 1.5 tons, whether you're doing 60 or 300 kilometers an hour. But there's a third part to this system that makes it even better: a blown diffuser. The air that's being sucked from underneath the car needs to go somewhere, and Lucas realized he could use it.
The air I suck from the area that generates great part of the downforce is then blown out as a blown diffuser, as the F1 used to do it in the past. You have a forced blown diffuser, which is, by the way, way stronger than a combustion engine blown diffuser from the exhaust. So you have a double effect underneath the car.
First, the air comes in under the front of the floor and gets accelerated through the tunnels. As that air speeds up, pressure drops, and that creates downforce. That's ground effect. Second, the fans are creating suction on the floor, pulling it down even harder, so more downforce. And third, all the air the fans are sucking up gets blown into the back of the diffuser, and that accelerates the air exiting the diffuser, which lowers the pressure even more. Now, you might remember Red Bull and other teams doing something similar back in the 2010s. They used exhaust gases from the engine to blow into the diffuser, and it made the car sound a bit weird. But it worked really well. But initially, these systems had a problem. It only worked properly when the driver was on the throttle. Off the throttle, the exhaust flow slowed down significantly, and so you lost that effect. Teams tried to get around this with clever engine mapping, keeping the engines revving high even when the driver lifted off the accelerator, hence the weird sound, but eventually it was banned. Lucas's system doesn't have that problem. The fans are electrically powered, so they work whenever you need them, regardless of the throttle position. And because they're more powerful than exhaust gases, the effect is stronger. So what does this constant downforce actually mean for the car?
It will be weird, but you have a constant, in this case, you have a constant 3G acceleration at every corner, at every speed.
Lucas is saying this is weird because from a driver's perspective, it is. For example, in a slow corner, a Formula 1 car might only pull 2G because there isn't much downforce. But in a fast corner, you might pull 5G because the wings and floor are generating massive downforce. So, as an F1 driver, you're constantly adjusting your driving. Slow corners feel completely different to fast corners. And if you have a change of wind speed or direction, the amount of grip changes massively. But with constant downforce, the car behaves the same everywhere. You always know exactly how much grip you have. And this constant downforce creates 4 big benefits. But before we get to those, I need to tell you about Brilliant, this week's video sponsor. Brilliant is an interactive learning app that teaches you to think like an engineer or programmer. You can explore topics like digital circuits, scientific thinking, or even programming with functions, all through visual, hands-on lessons. What I love is how it connects the dots between mechanical systems and logic. The same systems that make a car fast also make a good algorithm efficient. It's not about memorizing, it's about understanding how systems behave under pressure. You can start learning for free at brilliant.org/drive61. And Brilliant also give you 20% off an annual premium subscription to unlock everything they have to offer. If you love learning how things work, you'll love Brilliant. Right, so back to those 4 benefits of constant downforce. First, every part of the car can be optimized to the perfect strength with no waste. In F1, the suspension, the chassis, the wheels, they're all designed to handle peak load. And peak load happens only in the fastest corners, maybe around 5G. But in the slow corners, you're only pulling 2G, so those parts are essentially overbuilt. There's wasted material, wasted weight, because they're not being fully used at lower speeds. But with Lucas's car, because the forces are constant, you can machine every part to the exact minimum weight needed, with no waste. Everything is being used to its full capacity all the time. Second, the setup of the car can be optimal everywhere. In F1, because the loads through the car are different in slow corners versus fast corners, the suspension setup is always a compromise. But when the loads are constant, you can optimize the setup perfectly for that one condition. Third, the car is easier to drive. And I can speak from experience here. When you drive a high downforce car, there's a huge difference between the grip you have in a corner like Copse at Silverstone, which you take almost flat out at 180 miles an hour, versus a slow corner which you might take at 50. And that is more difficult for the drivers. Not to mention that winged grip is also affected by the wind itself. A gust or change of direction can completely change how much downforce you have from corner to corner. But if you've got constant 3G of grip, constant grip at every corner, then you always know what the car's going to do. And that means you can push that little bit harder and extract a little bit more speed. And fourth, this system works even when the car is sideways. In F1, as soon as you get past a certain yaw angle, when the car starts rotating, you lose downforce. The wings aren't aligned with the airflow anymore, so they just don't work as well. And if you go too far in a high-speed corner, you are just going off. But the downforce in Lucas's car doesn't care which way the car is pointing. So if you start to lose the rear, you've still got grip to catch it. And actually, you'd likely see the cars sliding around a little bit more than we do in F1, because the drivers know that they can slide around and still be fast. Now, the fan system is the headline, but Lucas made some other clever choices to make this car work. First, the wheels are covered. In F1, exposed wheels account for about 35% of the car's total drag. So by covering them, you're cutting a big chunk of drag down the straight. And there's a second benefit. In the rain, the covered wheels reduce water spray quite a lot, which means that full wets might actually get used. Second, there are no side pods. In F1, side pods have the radiators inside for cooling, but Lucas's car uses the air from the fans for cooling instead. So you don't need big radiators and side pods, which means less frontal area and so less drag. And third, it has a tiny rear wing. Because the ground effect floor and the fans are doing most of the work, you only need a small wing for flow management and stability, not the big drag creating rear wings you see in F1. So this is all great, but what do the numbers look like? This car has been through CFD, computational fluid dynamics, which is basically a digital wind tunnel. And here's what came out. It has a drag coefficient of 0.475. Now, a modern F1 car has a drag coefficient of around 0.85. So Lucas's car has roughly half the drag of F1, and that is a big deal for energy efficiency. Then the car has a downforce coefficient of 2.65. That's the amount of downforce generated. F1 cars are around 3 to 4. So Lucas has kept decent downforce while cutting drag. And the frontal area of the car is only 1.27 square meters compared to F1's 1.6. So that's the actual size of the car pushing through the air. A smaller frontal area combined with low drag means the car is really slippery. But there's one more clever bit, a modular battery. In most electric race cars, the battery sits behind the driver, like where a fuel tank would be in an F1 car. But Lucas has distributed the battery around the driver in smaller modules.
I wanted to move the center of pressure of the floor in exact on top of the center of mass from the floor battery.
The center of pressure is where the aerodynamic forces act on the car. The center of gravity is where the weight acts. And if those two are aligned, you get neutral balanced handling. And because the battery is modular, you can remove specific modules for qualifying.
So for qualifying, if you want to go even further in the simulation, then you take 170, 180 kilos out of the car for that 2 or 3 laps that you need.
It's actually similar to how F1 uses fuel. In a race, F1 cars start with 110 kilograms of fuel, but in qualifying, they run with just enough fuel for a few laps, maybe 10 kilograms. And a lighter car means faster lap times. Lucas's system does the same thing, but with battery modules. And as for the power, well, that's 600 to 700 kilowatts from twin motors, one on the front axle and one on the rear, so four-wheel drive. And that's not made up technology. Formula E's Gen 4 cars, which are coming in 2026, have the same setup. Now, all of this is interesting on paper, but the real question is, would it actually work? Well, Lucas worked with his, and briefly my, Formula E team, Lola, to find out. They ran the car through proper lap time simulation software by Canopy Simulations, the same as some F1 teams use. Lucas's first simulation was around Monaco, with the car in its quickest mode, with the fan, maximum power and the smallest battery. And the car lapped Monaco in 59.5 seconds. And these simulations at this level are very accurate. Now, compare that to Lando Norris's pole position from this year's Grand Prix, which was a 1 minute and 9.9 second lap. So Lucas's car is theoretically 10 seconds a lap faster. And when you look at the cornering speeds, the difference is clear. In the slowest, tightest corners, Lucas's car is significantly faster than F1. It's got that fan-derived downforce, which is good for low-speed braking and low-speed corners. Plus, the car is a bit narrower, which makes a big difference at Monaco. Then, in the medium and high-speed corners, there's not actually a lot in it. Now, this is Monaco, and Monaco is a slow circuit. I'd expect that through Copse at Silverstone or Pouhon at Spa, where F1 cars are pulling 5 or 6G already, the F1 car would be much faster. These corners need maximum downforce, and F1 cars have that. But Lucas's car isn't actually just optimised for Monaco, it's optimised for efficiency. And that means it might be faster than F1 at the very fastest circuits.
I would expect for tracks that have a higher average speed, the drag would be even more important. Because imagine in Monza, right? You would use the suction for the braking, the chicane. You probably would switch it completely off for the rest of the track. You would use it again for the second chicane, then for the Lesmos. You use it only in a few places. So maybe the car will be way, way more efficient than any car available today in a track like Monza or Silverstone.
And I think this is feasible. Monza is basically long straights and slow or medium speed corners. So use the fans in the braking and corners where you need it, but the rest of the time reap the benefits of the smaller frontal area and ridiculously low drag. Now you might be thinking that running the fans uses loads of power. And you'd be right. Those two fans are drawing 60 kilowatts combined when they're running at full power. And to put that into context, that's about the same as a small hatchback engine. The smallest 1 litre VW Golf makes around 66 kilowatts, so it's not nothing. But here's where the numbers get interesting. According to the lap simulation study, the fans are incredibly efficient. There's a 10-to-1 ratio. If you want to go faster around a lap, you can either add 10 kilowatts of motor power or just 1 kilowatt of fan power. The fan is 10 times more efficient at making the car faster. And when Lucas also ran the numbers for how effective the fans really are, so the same car with and without the fans, he found that without the fans, he'd need a third more energy to do the same lap time. Now, all of this sounds great on a computer, but could it work in the real world? Well, according to Lucas, yes, because all of this technology exists today, and because it uses existing technology rather than requiring years of development, Lucas reckons a prototype could actually be built for around $3 million. Now, the car's not in production, there's no race series for it, but it's not science fiction either.
I don't see any reason we cannot build this thing, and actually I want to build one. I'm actually in the process of trying to figure out how to build a prototype to start testing this.
So thank you to Lucas for sharing this interesting project, and thank you for watching. By the way, only 21% of viewers are subscribed, so if you're not, please check and subscribe. It really helps us get more interviews like this. Thanks again, and I'll see you next time.